hour about student activities, but that would seem pretty hypocritical. So I'm just going to talk for a few minutes here, and then we're going to do some activities, and we'll do them at a much quicker rate than I would do with my class for a couple of reasons. One is I want to make effective use of the 60 minutes we have here, and secondly, you folks already know a good bit about statistics, and so I trust that you're in a better position to discuss the ideas that the activities are getting at than the students are until they've gone through the activities more methodically. So we will be doing activities, but we'll do them more quickly than I would do with my students, and we'll do more talking about it and what the point was and how to implement them and things like that. The first session I did yesterday was about activities for analyzing data in an exploratory, descriptive kind of fashion. And then yesterday afternoon we talked about exploring randomness through student activities, and this morning we're going to talk about drawing inferences through student activities. Mostly we're going to talk about the concept of statistical significance, certainly an idea that came up in the first talk this morning. And we're going to present and do and talk about some activities for helping students get at the reasoning behind that concept of statistical significance. Thank you. Let's see, I've got my address, my email address there. If questions occur to you after today that you'd like to send my way or comments, please feel free to do so. I've got my web page there also, which has links to a bunch of teaching resources related to the workshop statistics book that most of these activities come from. So I invite you to check that out if you care to. I managed to get through the whole first page without an original thought, got through the address and all, and then I decided to quote from two statistics educators that have really influenced my thinking and my teaching. George Cobb's quote is so poetic that I just love to read it, so not to insult you, but George wrote, "Shorn of all subtlety and led naked out of the protective fold of educational research literature, there comes a sheepish little fact that lectures don't work nearly as well as many of us would like to think." I'd like to be able to say that quote inspired me to develop the activities I have, but actually I didn't discover the quote until pretty much after the fact, but it really does summarize what I try to do in the classroom and what I'll try to present for you here in the next hour. Less poetic, but very much to the point, Joan Garfield, who does a lot of research into how students learn statistics, and she has an educational psychology background, writes that statistics teaching can be more effective if teachers do two things. First of all, figure out what it is you really want students to be able to know, to be able to do and to know at the end of your course. And then secondly, design activities that help them develop that kind of knowledge and performance. So again, I hope that what I show you in the next hour will represent those sentiments well. On the second page, you can see sort of a table of contents. Again, but hopefully you'll see what I mean. We'll talk about wayward golf balls, and I'll just leave that as a teaser for you. So it's from which some of these activities and data come. Which is actually the very last sheet, the front page of the very last sheet. Can imagine he showed up himself at all these scenes and classified the crowds as jeering or non-jeering, but somehow or other he classified the crowds according to two variables: time of year, whether it was warm weather months or cool weather months, and then according to whether the crowd was jeering the person on or not. Remember, his hypothesis was that jeering would occur more often in warm weather, and sure enough, of the 12 cases that he examined in warm weather, 8 had a jeering crowd and 4 had a non-jeering crowd. And of the 9 cases in cool weather, only 2 had a jeering crowd, 7 had a non-jeering crowd. So the question, of course, that we ask when we do statistical inference is, do these sample data support his conjecture? Do these data give us support for the theory that jeering behavior is more likely to occur in warm weather? Now, what's the first thing we can do? Let's just look at the numbers. 8 out of 12 times when it was warm did the crowd jeer, which is 2/3. 2 out of 9 times when it was cooled in the ground here, which is 22% roughly. Sure enough, 2/3 is bigger than 2/9. But of course, that doesn't tell the whole story. There's random variation going on here. The question is this difference big enough that we can attribute it to his conjecture about warm weather and not just due to chance variation? Exactly the same question that the first speaker was asking about the difference in the survey results between the 2 different years it was administered. And of course, that's the question that statistical inference tries to address. In other words, statistical significance asks the question, how often would this happen by chance? If our answer to that question is, well, this would happen by chance pretty often, then we'd say there's not much reason to support the researcher's conjecture. If our answer is this would not happen by chance very often, that gives us reason to think there is something to the warm weather versus cool weather conjecture. Is that clear? That's the question that significance is all about. So how are we going to tackle the question then? We could jump in and do some permutations and combinations and do some formal probability and answer that question. With introductory students, I don't think that's a fruitful first attack. So what we're going to do is simulate this set of experiments over and over again. And we're going to see how often by simulation we get results this extreme. How are we going to do the simulation? We're going to use playing cards. I'm going to give each of you 21 playing cards to represent these 21 incidents. We're going to assume that there were 10 jeering incidents and 11 non-jeering incidents. In other words, we're going to fix those marginal totals. You're going to take these 21 cards, 10 of which represent jeering crowds, 11 of which represent non-jeering crowds. You're going to shuffle them up real thoroughly and randomly deal out 12 of them to represent the warm weather months. And you'll keep track of how many jeering crowds were assigned to the warm weather month for that repetition of the simulation. Is that clear? And if you get 8 or more, then you've got a result that's as extreme as the one the researcher actually found. If you get 7 or fewer, you've got a result that's not as extreme as the researcher actually found. Okay. This will make more sense when you get the cards, I think. I've got the cards set up, and I think I did this right, so that you should get a packet that has 10 red cards and 11 blue cards. I'm not talking about the suits of the cards, I'm talking about the backs of the cards. So you need to focus on the card back, please. And the first thing I'd like you to do is count your little packet and make sure you in fact have 10 red backs and 11 blue backs. Make sure I counted correctly. Again, you want to look at the backs, not the actual suits. First thing, please make sure you got 10 red backs and 11 blue backs. 3 more. Thanks. Shuffle them up real well. And then just deal out 12 of them to represent the warm weather months. And keep track of how many red cards you have among those 12. Red cards representing jeering crowds assigned to warm weather. Okay. Repetitions of this experiment. Each time, keep track of that number of red cards assigned to the warm weather. Red cards among the 12. Okay. So repeat it a total 5 times. Shuffle them up real well in between each time. Please.
This misses the point.
Pardon me?
This misses the point.
What point's that?
Does jeering have any effect on whether they jump?
Yeah, that's true. I don't have that information. That's a, yeah.
Is jeering effective? How about, have you done the research of how many times you need to shuffle? Like 21 cards?
I have not done that
Or is it
research.
cleanly, sorted?
Open problem for the workshop participants. Probably. It's only 21, so you would think there'd be less.
It's like it would.
Okay, so you're repeating this 5 times each, please. Once you've repeated it 5 times, what I'm going to ask you to do is come up to the board and help me create a dot plot of the number of jeering crowds assigned to the warm weather months. So once you've done this 5 times, please come up and put dots representing your 5 results on the axis I've drawn.
The other question is, how often do you have to break up poker games during this activity?
Get our car there. Yes.
You don't have to repeat it.
So you're putting it here. Yeah, the warm, the red. You're using a blue pen. Oh. I'm confused.
It is confusing.
I know.
Bad choice on my part. You're creating a dot plot of the number of red cards among the 12, even though you're doing it in blue marker.
I don't regret.
Yeah.
This and I thought, am I doing this right?
Well, it's pretty bizarre. 6, 6, 4, 6, 6. Okay.
Want the cards back, or we have something else?
I'll take him back. the rubber band.
Students are walking away with the rubber bands now, so.
Gonna shoot you, Mark.
Thought I wouldn't have that problem with this group.
So how do you do this with a class of 70 students?
I don't. That's my easy answer. If you're organized enough and have some assistants, you might be able to.
They can bring their own decks
Yeah.
or something.
Have them do it outside of class before.
Instead of a graphing calculator, having like decks of cards, dice, coins.
So what we should be looking at as the dot plot is being constructed here is how often, just by chance variation, do we get a result that is as extreme as the researcher actually found. And the researcher actually found 8 jeering crowds in the warm weather. And we've already said 8 out of 12 is sure enough bigger than 2 out of 9. But is it enough bigger that we can decide it's not likely to have occurred by chance alone? Well, that's exactly what we're investigating here by having repeated this experiment over and over again by chance to see how often chance variation would give us such an extreme result. In a minute here we'll have not quite the answer, quote unquote, but we'll have a sense of the answer. I've done this several times now, and I never cease to be amazed at how normal looking this plot ends up looking. I mean, we don't have a normal distribution. We don't even have a binomial distribution. We've got a hypergeometric distribution with a pretty small sample size. And yet the sampling distribution still turns out to be pretty normal, which I still find remarkable and oddly comforting in a way. So what's the answer? How often did we get a result as extreme as the researcher found? Again, the researcher found 8. So that happened 1, 2, 3, 4, 5, 6, 8 times out of how many repetitions did we do here? Now let's not count all the dots. Let's assume you all did it 5 times. So there's 17 of you. 17 times 5 is 85. So a little less than 10% of the time. So it's not real common to get such an extreme result, but it's not real rare either. It's sort of in the middle range. So my point here is a couple of things. One, that even in this non-typical situation, this isn't a situation where you can easily plug in a z-test or a t-test. We could do a chi-square test, but we've got a pretty small sample, so that approximation wouldn't even hold all that well here. So even in this strange situation, we can still get a sense for what significance is all about. Significance is about the question, how often would the result happen by chance? And by simulation, we've seen that it would happen maybe a little less than 10% of the time. We could follow up and do something more formal to get a more accurate estimate of that p-value. Of course, what we're talking about here is the p-value of the test. The p-value tells you how often the observed result would happen by chance alone. And based on our simulation, we estimate the p-value is a little less than 10%. So my point is not to do any formal hypothesis test at this point, but to try to introduce students intuitively to the notion of what significance is all about. First of all, just the fact that we don't conclude because 8 out of 12 is bigger than 2 out of 9. We don't conclude automatically the researcher's conjecture is correct. We realize that there's sampling variation, that might have happened by chance alone. Just that very realization is a big step to help students to take, I think. And then how do we address the question of how often it would happen by chance alone? We can simulate it and get a rough sense for it. Questions on the activity? I'd like to do a little bit more with the activity with you folks that I don't do with my students. But just since we all appreciate the mathematics that's underlying this, why don't we take a few minutes and do the mathematics? We can figure out the exact probability of having gotten 8 or more here. First of all, were there any of these numbers that I need not have put on the display? Could we have gotten 10? Yeah, we could have gotten 10. Obviously, it's a rare event, but we could have gotten 10. Could we have gotten 11 or 12? You only had 10 red cards, so you weren't going to get 11 or 12. Is there anything on the low end we could have eliminated? We didn't get any ones. Could we have gotten a 1? Could have gotten a 1. Could we have gotten a 0? You only had 11 blue backs, and you were dealing out 12 of them, so we weren't going to get a 0. That's kind of interesting to note, and students might even appreciate noting that. Let's figure out the exact p-value here. And incidentally, this test is sometimes called Fisher's exact test. I'm not recommending teaching that test in an introductory course, but just the notion behind the idea of significance is what I think is important for students to get a sense of. The Fisher's exact test asks, let's just do the counting and figure out the denominator, the total number of ways you could have dealt out these 12 cards among your 21. And then the numerator will be the number of ways we could have gotten a result as extreme as in the actual data. Try that. Let's do denominator first. How many different ways could you have dealt out these 12 cards from your group of 21? Yeah, it's just the binomial coefficient, right? 21 choose 12. Number of ways of choosing 12 cards from the 21 that you had at your disposal. Now let's ask, how many ways could the result have turned out as extreme as in the actual sample? So first of all, how many ways could we have gotten 8 red ones? How many red ones did you have? You had 10 red ones in your pack. So 10 choose 8 ways to get the 8 red ones, but then how many ways to get the remaining blue ones? You had 11 blue ones to choose from, and if you had 8 red ones, since you were doing out 12, that meant you had 4 blue ones. Times 11 choose 4. And again, I want to be clear, I don't go through this analysis with my students, but I thought, since we all appreciate the mathematics behind it, it might be fun. But that's only one way to be as extreme as the data. You could also have gotten 9 red ones. How many ways to do that? 10 choose 9, times 11 choose 3. You had 9 red, that means you had 3 blue. Finally, you could have, it didn't happen at all in R85, but it could have happened that we got all 10 red. 10 choose 10 times 11 choose 2. I can take my word for it. To 4 decimal places, this is between 5 and 6%. So our simulation actually turned out to be a little bit high in its estimate of the p-value of this test. We kept doing it over and over and over again in the long run. About 5.6% of the time would we get 8 or more red ones out of this one. Any questions on the activity? Again, I want to be clear that my point is not that I do these hypergeometric calculations with students. The point is to try to get at the idea of what significance is all about. Namely, asking the question, how often would this happen by chance alone? We could turn to the computer to do the simulation. And I sometimes do that with students, but I always like to precede technology simulations with physical simulations. It's already one cognitive step to appreciate having the cards represent these crowds, and red cards representing jeering crowds and blue cards representing non-jeering crowds. That's already one cognitive step. It's another step, and I think a bigger step, to have computer output representing these crowds being simulated over and over again. So my hope is that by at least the first time through, doing it literally hands-on, students can then better appreciate that this is simulating a certain process, and then when you have the computer do it, hopefully they can match up better what the computer is doing. Questions, comments?
Yeah, I like the cards. Start off with the computer, but people still have this impressive. How does the computer move?
Yeah.
You're shuffling everything, so you feel that.
Nope.
Especially to your hands.
Right. It's not rigged ahead of time. I pretty much knew it was going to turn out like this because I know the probability behind it, but it would have turned out however it turned out. Okay, the next activity I'd like to present to you, with you, deals with decision dilemmas, is what I called it. And I gave you very little information about it on the handout because we're going to do it and then talk about what we did. And what I'm going to do, with your indulgence, is ask you to answer 2 questions, 2 not real sensitive personal questions. So I'm just going to ask for a show of hands when we're done with this. Got a little half sheet of paper for you. Just go ahead and read over the questions and mark down your answer. First question's a yes or no, the second question's an A or B. We'll just do a show of hands when you're done. So everybody jotted down their answers. Another. Prince Rossman questions. Would one of you please read your version of the question? John?
Imagine that you have decided to see a play and paid the admission price of $20 per ticket. As you enter the theater, you discover that you have lost the ticket. The seat was not marked and the ticket cannot be recovered. Would you pay $20 for another ticket?
Everybody clear on the distinction here? In both cases, you're out $20 from what you thought you had 5 minutes ago. And the question is, do you buy a ticket to the play or don't you? The only difference is in one case, you've lost the $20 bill you thought you had. In the other case, you've already paid for the ticket and you've lost the ticket. But either way, you're out $20. And the question is, do you pay $20 for a ticket to the play? So it's a similar scenario. It's a little bit different in terms of its psychological impact on the person making the decision. But in terms of the actual finances, it's exactly the same scenario. And of course, the question is, do people respond differently depending on the type of scenario they're in? So I'm going to ask how many of you answered yes, you'd pay the 20 bucks for a ticket. How many of you answered no, you wouldn't, depending on whether your version dealt with a lost ticket or a lost $20 bill. Clear? You know which of these two situations you're in? Of those of you that had the question about the lost ticket, of just those of you, how many of you said yes, you'd pay the 20 bucks? 1, 2, 3, 4, 5, 6, 7. How many of you said no, you wouldn't? Just 2. For those. And those of you who got the lost. And I'll have to ask you to take my word for this. What usually happens is that people who have lost the ticket are less inclined to go ahead and purchase another ticket. Kahneman and Tversky are the psychologists who are famous for doing research into how people make decisions in the face of uncertainty and heuristics and biases that people apply when they're dealing with uncertainty and randomness and probability. And they've done many studies like this and some on the very same question. And it didn't work at all with this group for some reason. Usually the lost ticket people are much less inclined to be willing to pay $20 for another ticket. I guess.
I have gotten that out of this chosen no.
You would have chosen no. I'm sorry, you didn't get that one. I did this last week with the workshop, and the results were really strikingly different. And Kahneman and Tversky have done lots of studies with large sample sizes where the results are pretty different. So I apologize that it didn't work very well here, depending on how you define work very well, of course. But my point is, one could come back to a similar activity to what we did with the cards and the suicides, and ask how often would such a difference occur by chance alone. In this case, we don't need to because these are so very similar. In fact, we've got a slightly higher percentage of the lost ticket people who said they'd buy a ticket than of the lost $20 bill people. So there's no reason to do a test here. But if it had turned out a little bit differently, if it had been 2 and 7, say, then we could reasonably ask, well, we got a difference in the direction that was conjectured. Is it a big enough difference that it's unlikely to have occurred by chance? And then we could turn to a computer to simulate it, or we could turn to the playing cards to do exactly what we did with the suicides, but with this question instead. Peter?
There's two psychologists.
Kahneman and Tversky. Daniel Kahneman and Amos Tversky. Tversky just died a year or so ago. There's an excellent article, a summary article by a gentleman named McKean that appeared in Discover magazine. I'm not going to be able to give you the exact reference, but I think it was 1985. The article is called Decisions. Discover magazine sometime in the 80s. Psychologists were Kahneman and Tversky. And their definitive work is a book called Judgment Under Uncertainty, Heuristics and Biases. Okay, on to question 2. You're probably guessing that some of you have different versions of question 2 than others. So would somebody read one version of question 2, please? Lori?
Imagine that the U.S. is preparing for the outbreak of an unusual Asian disease which is expected to kill 600 people. 2 alternative programs to combat the disease have been proposed. Assume that the exact scientific estimate of the consequences of the programs are as follows.
Let me interrupt you right there. Everybody has the same thing so far, right? So the only difference is about to come.
If program A is adopted, 400 people will die.
Program A, 400 people die. With B, 1/3 chance that nobody dies, 2/3 chance that 600 die. Somebody who had a different version, would you just read the consequences part of it, please?
Program A is adopted, 200 people will be saved. If Program B is adopted, there is a 1/3 probability that 600 people will be saved, and 2/3 probability that no people will be saved.
Everybody agree these are the exact same options? Nothing happens, 600 people die. You choose program A, well, in one scenario 400 will die, in the other scenario 200 saved. Well, that's the same thing, right? Just different than the ticket, where it's a little bit different psychologically. You lose a ticket or lose a $20 bill. This is different in that the scenarios are exactly the same. 1/3 chance nobody dies is the same as the 1/3 chance 600 saved. 2/3 chance all die is the same as 2/3 chance nobody saved. So it's exactly the same scenarios. What's different about it? Yeah. In one case, you read all about dying. In the other case, you read all about saving. And what usually happens, let me be bold and tell you my conjecture ahead of time. Most people who are presented the die options choose B. Most people who are presented the save options choose A. Sounds like a great thing for 200 people to be saved, for sure. Doesn't sound like such a great thing for 400 people to die, for sure. Well, I'm not real optimistic that you folks follow the trend that most people do, but we'll give it a shot. So the difference here is some of you read about deaths, some of you read about lives saved. Your choice was program A or program B. Again, my conjecture is those of you who read about deaths are going to be more likely to choose B, but I could well be wrong. How about the deaths people? How many of you chose A, please? 4 of you chose A. Deaths people, how many chose B? 1, 2, 3, 4, 5 of you chose B. So slight preference for B among those who had the consequences presented in terms of deaths. Those of you who had the question phrased in terms of lives saved, how many chose A? 1, 2, 3, 4. This worked very well last week on a group of faculty. I've never actually tried it on students, but I've had other faculty say that it works very well on students. So if you have the courage, I encourage you to do something like this with your students. But again, the statistical point, I like this example for many reasons. One is that we're talking about doing surveys well, and some cautions involved when doing surveys and how important it is to be careful in how you word the questions. One neat thing about the experiment is that this is an experiment. It's a controlled experiment. We have two groups, and I actively intervene in the process to randomly assign each of you to be in one group or the other group without your knowledge. I admit that there is an experiment at work here, but it's an experiment about how to do surveys well. And if one followed up by doing some kind of card simulation or something, we can introduce the ideas of significance and statistical inference in the context of this little experiment. Enough said? Sorry, it didn't work out better. You folks are too sophisticated in your decision making. Okay, the third example I want to look at is one that hits very close to home, literally for me. If you look at the very last page of the handout, I talk about a naive teacher of statistics. Does anyone guess who this naive teacher of statistics is? So this is an autobiographical example here. My wife and I last year moved to a house on a golf course. To discover to our chagrin months later that it was in a prime spot for poor golfers to hit their golf balls. It's on a long par 5, about 150 yards off the tee to the right-hand side, so people try to kill it because it's a long hole, and since most right-handers tend to slice off to the right, we get an awful lot of golf balls in our yard. So we've been collecting balls for about a year now, and we counted them a couple weeks ago, and the counted them according to the identifying number put on the ball. Those of you who aren't golfers, you may or may not know the golf balls typically have numbers on them. Typically number 1, 2, 3, or 4. And when I went through my collection, I found 137 balls that had the number 1. 138 balls had the number 2. 107 balls had the number 3. 104 balls had the number 4. And there were a bunch of others. 14 either had bigger numbers on them or didn't have any numbers on them, or were novelty balls of some kind or other. Notice the total is 500. You might be asking, did I go out and take the first 500, or did I, by some miracle, happen upon 500? Well, when we finally sat down to count them, we had 499. That was just such an unusual number, I didn't want to stop there, so I just went out in the backyard and picked up one more and had myself 500.
500 over what period of time?
Over a year. We get a lot of balls, and there's probably 3 times as many that people come into our yard and pick up themselves. We get a lot of golf balls. I'm not proud of it, but it's an interesting little example. So the question I had was, are golf balls as they're deposited in my yard uniformly distributed among the numbers 1, 2, 3, or 4? Looking at the data, for some reason we got more 1s and 2s than 3s and 4s. But of course the question that statistical inference asks, which we've asked for the last 45 minutes here, is this difference big enough that we can attribute it to some systematic thing and not just due to the random variation that occurs when golf balls arrive in my backyard? How often would this happen by chance is the question of the day, again, for these data. And I like this example because, again, it's not a real standard example. We can't just do a z-test or a t-test here. We could do a chi-square test, but I'd rather take a different tack with it. I'd like to ask, how can we simulate this process and then decide whether or not our simulated result is as extreme as this result? With the suicides and the cards, it was pretty easy to define what we meant by as extreme. If we had 8 or more red ones, it was as extreme as what the sample was. But this time, it's not as clear-cut what the test statistic should be. So I'm going to ask you to come up with some suggestions for what the test statistic should be. But before I do that, why don't we turn to Minitab to do this simulation. This time it'd be too difficult to simulate this with any physical process, I think. So if I can get this machine to work, I'll ask Minitab to do this. If you're familiar with Minitab, by all means follow along. If you're not, I certainly don't intend to teach you Minitab in the next 15 minutes, so if you just follow along at the front here. Those of you that are comfortable with Minitab, if you'd like to recreate this, that's fine. So Minitab is under the mathematics folder, I believe. Let me put the results up here again. Okay. So how can we simulate this? What do we want to simulate? We want to simulate golf balls arriving in my backyard. There were 500 of them, but 14 of them didn't really fit into my classification scheme. So I'm going to simulate 486 golf balls, assuming that they are uniformly distributed among the integers 1, 2, 3, 4. So how can I do that? If we go into the Calc menu, choose Random Data, and then Integer, because we want integers 1 through 4 uniformly distributed. So Calc Random Data Integer. And again, it's perfectly fine just to follow along with the screen. And then we want 486 of them. Again, why 486? The 500 minus the 14 cases that didn't fit my classification. Store it in column 1, C1. The minimum value, the values are between 1 and 4, we're assuming. So 1 for the min, 4 for the max. Okay, to proceed. And it'll take it, well, it didn't take it too long. So in column 1, we've got 486 golf balls, if you will. First golf ball had number 3 on it. Second one had number 4, a 3, a 1, a 4, and so on. So it'd be awfully handy if we can tally that up and see how many 1s we have, how many 2s, how many 3s, how many 4s. We come up to the session window at the top and say tally C1. It'll tell us how many we have of each number, hopefully without too much effort. So for this simulation, assuming a uniform distribution, we got 116 1s, 138 2s, 110 3s, 122 4s. So the interesting question now is, and this is not a question we had to deal with the cards, how do we decide if this simulated sample is as extreme as the sample I got in my backyard? It's not so obvious what the test statistic is. If we're doing a chi-squared test, we take the sum of observed minus expected squared over expected. But where in the world did that come from? That's not intuitive to most folks anyway. So I'd like you to please suggest a more intuitive, more simple and intuitive test statistic that we might use to decide if this sample is as extreme as that one. Ideas? Here? Okay, we can compare the sums of 1 and 2 to the sums of 3 and 4. And it would be as extreme if this sum was bigger than that sum. I hadn't thought of that. That makes sense. Other ideas? Even simpler. Pardon me? Okay. And then like add the differences or something? Yeah, we could take, the expected count is 486 divided by 4. We could just look at the absolute differences and then add them up. Very reasonable test statistics. Sort of like the chi-square, but without the squaring and dividing part. So a very reasonable test statistic. I want something even simpler. I want something really simple. Doesn't quite do the job as well as the two that have been suggested, but really simple. Look at portions of each and then do something to them. I think it's still simpler even. I think it's so simple that you're embarrassed to say it's so simple. How about if we just look at the maximum count? The maximum count I got in my backyard was 138. We could just see how often our simulated sample gives us a maximum of 138 or more. And granted, that's not a real good test statistic. It's ignoring all the other information. But it's a first intuitive approximation. It's not a horrible thing. Or if we want to make it a tad more complicated, we could look at the maximum count and the minimum count and look at the difference. In my backyard, the max minus the min. Try to do blue for the actual. In my backyard, the max minus the min was 31. In this simulated sample, the max minus the min was 28. So using that as our test statistic, this simulated sample was not as extreme as the actual sample in my backyard. So what's the point here? A couple of things. The same point as before, that significance asks, how often would this happen by chance in the long run? But here we've got the added complication that it's not clear-cut what as extreme as what actually happened means. So I think it's worthwhile to ask students to suggest some reasonable measures, whether you look at the max, look at the min, look at the max minus the min, look at deviations from expected, look at a couple of categories and add them and compare it to another couple of categories added. All are reasonable, some are better than others, some are simpler than others. But all are reasonable for getting at the idea of significance. How about if we do this a bunch of times and then see, why don't we choose max minus min is pretty simple, but it's not completely ridiculous. Why don't we choose max minus min for our test statistic and see how often our simulated samples will give us a test statistic as big as 31. If the answer is it happens awfully, awfully rarely, then I've got evidence that I don't have a uniform distribution arriving in my backyard. If the answer is it's not so very rare, then I don't have evidence that I have anything other than a uniform distribution in my backyard. So let me come up here and get Minitab to simulate this a whole bunch of times. We don't really have time for a whole bunch, but we'll do it 10 or so times. I want to generate integer data, 486 rows. Let me ask for it 10 different times, so I'll tell it column 1 through column 10. Still with a min of 1, still with a max of 4. We'll take it a minute or two. And we'll tally those up. Still working out. Not sure why this is tough for it, but it's taking a little while. While that's working, I want to pass out a handout. Pass these back, please. Still working. Well, maybe we should come back to Minitab when it's ready for us. Let me describe what I just handed out to you. Another similar application to the golf balls, an example that calls for a chi-square test, but where you can do simpler things like this to get the basic ideas across. And an interesting question, I think, is the question of whether people's days of birth are uniformly distributed among the 7 days of the week. It's easy enough to ask students to collect this data. Just give them a calendar like I've given you. And I'll ask each of you to please figure out what day of the week you were born on if you don't already know. So you can use the index in the upper left to find which calendar applies to your year of birth. And then check out your birthday and see what day of the week it was on. We don't have a big enough sample here to be able to see any big differences. I don't think that if you had a bigger sample or if you asked students to go out and each talk to 5 friends and figure out their birthdays, you might have a big enough sample to see something going on here. Has everyone figured out their day of birth? How many of you are born on Monday? No hands? Just 1, 2 Mondays? Tuesday? 1, 2. Wednesday? 2. It's pretty uniform. Thursday. I'm a Thursday also. 2 Thursdays. Friday. 3 Fridays. Saturday. Wow. 4. And Sunday. 3 Sundays. 5 Saturdays. That's interesting. For such a small sample, I would guess that this isn't big enough. There's nothing there to indicate a non-uniformity. With a larger sample, if we had 100 students or 100 people, we might be able to see some interesting things there. What I'm told has been happening is that with younger people, there's a clear...
Yes.
Yeah. You think there's going to be a lot there or not so many there?
Not.
Not so many there, right, exactly. I'm told that since births are being scheduled more and more often now, and since doctors don't like to schedule work for themselves on weekends, with younger people you can really see a difference with Saturdays and Sunday births not happening very often. Interesting little study you can do. And the point, of course, is you can get at questions, issues of statistical significance. How often would such a departure from uniformity occur by chance alone? With a bigger sample, we can get at it. You can introduce the chi-square test, or you can do something more basic to get at the basic idea like we've done with these golf balls. Many tabs now ready for us. So what we're going to do is go through these 10 simulated samples and see how many of them have max minus mins that are as extreme as in my backyard. So in this first sample, the max is 132, the min is 110. So the difference is 22. Please check and make sure I don't mess up anything here. The second sample, 139 minus 101, so 38. And what was it in my backyard again? 138. 31, so that one was more extreme than in my backyard. And column 3, 24, 133 minus 109. Column 4, 24, column 5. Yeah, that one's awfully uniform. 16, column 6, 21. Column 7. Seven's a 21. Column 8. 22. Column 9. 29 minus 116. 13. Column 10. 5. Obviously, we'd have to do this more than 10 times to get a sense for the sampling distribution. Sampling distribution of an unusual test statistic. But of these 10 times, once did we get a simulated result more extreme than in my backyard. So if we did this 100 times, we'd have a better sense for what the approximate p-value, if you will, of the test is. In other words, a better sense for how rare it is to have gotten such a departure from normality as I got in my backyard. So my point with these activities is just to introduce the basic reasoning behind statistical significance, trying to emphasize to students that significance is about that question, how often would this happen by chance? Which one can investigate by doing some physical simulations, some computer simulations, and the like. So, questions, comments?
You do the same thing with lottery numbers and so on. What the best number would be.
Exactly. Any other thoughts, questions? Thanks very much for your attention.